My name is Steve Miner. First, I want to thank the organizers for putting on another great conference, well, at least so far, but it's been good. And today, I'm going to try to have some fun with juggling patterns and programs. So first, I'd like to tell a little story about a young boy who loved juggling. His father taught him a few tricks, and after lots of practice, he was ready to perform in front of a crowd. So here's some old video. This is a little bit fuzzy. It's from 1983. Let's take a look. Oh. There we go. All right. So if you're a juggler, you'd be pretty impressed. This is a 9-year-old boy. I think you already guessed who it is because I slid my slide, but that's not me, although I do have those shorts. But this is Anthony Gatto, who even at 9 years old was a world-class juggler. He traveled the world for the next 30 years, worked for Cirque du Soleil in Las Vegas and Orlando. A few years ago, he retired from juggling, performing. He's now running a concrete business in Orlando. But he was a world-class athlete. I mean, just tremendous skill, set a bunch of world records. So that's just a warm-up for what people can do in juggling. Maybe you may be wondering, okay, juggling, that's cool, everyone likes that. But how does that connect to Clojure? Why are we at a Clojure conference talking about juggling? Well, I wasn't the first one to make the connection. You remember this guy, Rich Hickey, back a few years ago, had a great talk, Simple Made Easy. And part of that talk, there was just one slide, but he mentioned juggling. And he said, you know, this is a problem for us when we're talking about mutable state, complecting time and value. Intertwining things makes it hard to understand. And that complexity makes it hard for us to reason about our programs. And he used juggling as an example of complexity. So I want to give you a metaphor alert. So Rich was talking about juggling in terms of incidental complexity. I'm going to change it. I'll put my own spin on juggling. I want to talk about juggling as essential complexity. Sometimes we want to do difficult things, complex things. We want to approach something. Maybe it's just a challenge. Maybe it's a business reason. But things are hard sometimes. And I want to look at juggling as an example of something that's hard to do. But if we look at it deeply, maybe we can get some insight into finding some inner simplicity within that complex task. So for me, juggling is going to be our main task, and see what we can learn from juggling. Now, to help us get started, I'm turning to one of the great men from computer science and electrical engineering background, Claude Shannon. You may have heard of him. He's known as the father of information theory. He contributed a lot to digital circuits way back in the 30s. In the 40s, he worked with Alan Turing for a while in cryptography. Just made tremendous contributions all across the field and anticipating digital computers and communications. Later, he spent most of his career with Bell Labs, but later in life he was a professor at MIT, and he was also a member of their juggling club. So as just a really smart guy who enjoyed juggling, he decided to write a paper called The Scientific Aspects of Juggling. You can find it on the web. I'm not sure when it was published. It was supposedly written in the 1980s. It's in his collected works published in 1993. It may have been out there sooner. But we're going to take a look at some of Shannon's ideas about juggling to try to get some insight into that. So Shannon starts with the history of juggling. And of course, it turns out every talk on juggling that mentions history at all is going to show this graphic from the Egyptian wall painting showing people juggling. So we know juggling was popular 4,000 years ago. And probably it goes back a lot farther than that. Shannon didn't mention this, but the New Yorker did some research and found that cavemen were juggling. So that's even farther back. So Claude Shannon was trying to come up with some insights into juggling, and he started with a simple form of juggling he called uniform juggling. So that's one throw at a time, alternating hands, and a constant rhythm. So now we can do a little demo. see. All right, so live demo. So the basic idea is we're just juggling. This is a simple 3-ball cascade. You can kind of feel the beat frequency, just every beat, throw one ball, catch another ball, and it's alternating hands. And the height doesn't really matter, all right? We can go a little bit faster here, but it's basically the same idea. Okay, so thank you. So anybody can learn to juggle like that. When we talk about the constant rhythm, you can see some tricks kind of change the rhythm. You can see a syncopated beat as I'm throwing one ball over a little higher, but trying to keep the other ones going. Okay, so that's a little bit beyond what he is talking about. Or if you're like crossing hands, that changes the rhythm. So real jugglers go past this uniform juggling, but you always come back to that simple pattern. So if we do an analysis at the simple level, that gives us a good insight, and we'll see how to connect that to all the other juggling tricks. Okay, so I just talked about the 3-ball cascade that I was demoing there. Is a simple thing. It's a crossing pattern. So odd numbers of balls, you do in a crossing pattern. Even number of balls, we do half of them in one hand, half of them in the other hand. So we're still alternating the throws, but the balls kind of live in what we call a fountain pattern, and they just stay on their side. And this is kind of the simplest low-energy way of juggling. This is what you should normally learn. So Shannon looked at juggling and came up with Shannon's juggling theorem. And in this, the interesting elements are the flight time. That's the time the ball's in the air. The dwell time is how long the ball is actually in your hand. Vacant time, your hands, after you've made a throw, the hand's empty for a fraction of a second. And of course, the number of balls is what we care about mostly. Keep that up. And H stands for the number of hands. Okay, so this is Shannon's theorem, and it really is a nice, simple equation that gives you the essence of juggling. Okay, but it also points to why juggling is hard. Okay, so I'm calling this complex made hard. So what we want to do is see how many balls can we juggle. And it turns out you can't do that much about the dwell time and the vacant time. A really good juggler can have a pretty quick dwell time, but the main thing, if you want to juggle more balls, you're going to have to throw them higher, get a longer flight time, which means throwing higher. Now, the flight time, actually, though, because of physics, we're dealing with gravity, the flight time is proportional to the square of the height. So as you get more balls in your pattern, you're throwing higher and higher. So to double your flight time, you have to quadruple the height you're throwing. And the problem in juggling, of course, small errors and compensations, it's a coupled system, things compound, and it gets hard fast. So there's a lot of us, almost all of us can learn how to juggle 3 balls. 5 balls is a pretty good juggler, okay? So some competent 3-ball jugglers might take 6 months of hard practice to get up to 5 balls. When you start getting to 7, you're really a dedicated, ready to be a professional juggler. And the world record for a sustained juggle is 9, although people have done up to 13 balls for a short period. So anyway, it gets hard fast. And I can see why some people think that's a good metaphor for complicated software. But there are ways to think about the juggling problem that might bring back a little simplicity. So we'll get to that. One other little curiosity. When I first saw Shannon's theorem, I was thinking, H, most jugglers, 2 hands. That's the usual thing, right? But of course, Shannon was thinking beyond me, and he said, think about our juggling troupe. It's the Flying Karamazov Brothers, a lot of fun. I don't know if you've ever seen them, but there's some videos on the web, and I've seen them a couple of times in person. They're a great group. So of course, when you get a group of 4 jugglers sharing clubs, we're scaling H. So it's possible. You just have to think about your problem. There are ways to make things work. Okay, so back to the theorem. Shannon also gives a good proof of the theorem. I don't have time to go through the whole proof, but you can kind of think about it a little bit. Think about the experience of the balls, right? So a ball is either in a hand or it's flying in the air, and it does that kind of per hand basis. And think of the experience of your hands. A hand either has a ball or it's vacant. And that's, if you think about the whole pattern, that's a per ball basis. So Shannon just multiplies those out and finds the equivalence because it all happens at the same time. And he proves it a little more rigorously than I just explained it. But still, it's a nice, simple equation. And I think that's very valuable when we're thinking about our software to try to find the essential simplicity that we can look in there. And one other thing you might notice, Shannon doesn't talk about physics directly here. I mean, he has a discussion about why flight times are the way they are due to gravity. But that doesn't appear in the equation. It doesn't talk about the weight of the ball. It doesn't take into account wind velocity. There's lots of extraneous details that aren't covered here that would matter if you're in those situations. But he's coming at it from the experience of a juggler in a kind of a normal juggling context. Okay, and so that's another, maybe something valuable you think about when you're designing your software. Start with what's essential and what's important. Don't be distracted by all these crazy possibilities. I mean, we do have to think about edge cases, but try to get the basics right first. So let's review some lessons from Shannon. So in his paper, he did a historical analysis. He thought about what jugglers have done before. He talked about some great jugglers in the past. I think that's also a valuable lesson for us when we're doing our software. We're facing problems. A lot of these problems have been faced, or similar problems have been faced in the past. It makes sense to review the literature a bit, just to get a feel for how other people have solved these problems. Maybe they didn't have the same technology, but you'll maybe get an insight by just looking through history. Okay, so that's kind of informal, but a worthwhile endeavor. The second point, domain understanding. Okay, so Shannon is a brilliant mathematician. He could probably walk up to any system and just say, okay, here's what's important, here's how the numbers work. But it helps to actually be in the domain, know something, have some experience of the thing you're trying to model. And Shannon was a juggler. He had a long history of juggling and tinkering. He even built juggling machines way back when. And that's fun. You can find those on the web too. So he had a domain understanding before he decided to do his deep analysis. Or for us in software, it makes sense to understand how the practitioners were modeling some kind of financial system or simulating something in the real world. Try to get out there and experience that directly before you start writing code. That might help you meet the needs of your users or do something that's more realistic. Now, the third item here, choosing the right abstraction. That's a really hard problem. I was going to say I don't have that much to help you choose the right abstraction, but if you're here yesterday for Eric Norman's talk, you know one way to approach that is by starting with a physical metaphor. And juggling is a great physical metaphor. Okay, so that's part of the reason I like this connection. Doing something physical, you're engaging different parts of your brain. Okay, you kind of know how things are going to work just by feel. And juggling will develop. If you practice a little bit of juggling, you'll get that feel for where the ball is going. You don't actually watch the ball. You can just know from your throw. You maybe look at the tops of the ball, but the idea of a physical metaphor, I think, is a really great starting point for approaching software, and I'm really curious to see how far that goes with Eric's work. Then the final thing is once you come up with this analysis, Claude Shannon's theorem really exposes some of the trade-offs when you're juggling from the experience of a juggler. All right, so we said he chose the right abstraction, he found simplicity, and he exposed the trade-offs. And I think that's a valuable approach for doing our software. Sometimes we get too caught up in like, oh, I can get an answer on this path. I'm just going to pursue one path. I'm just going to make everything work along that path. And sometimes we have to, I'll have to just fill that in and just do this. And we can be too focused on kind of get tunnel vision. It's good to explore trade-offs, design a system where you can turn some knobs later, but keep it within the experience of the common user or the practitioner in the field. If you're modeling something that has like a physical reality, try to think about trade-offs within their experience and model that in your software. Okay, I want to turn to another paper. This paper is a Scientific American paper that came out in '95. Beek and Lubel, and they knew Shannon. They refer to Shannon. But for me, this is the earliest reference I could find that had a description of Siteswap notation. And this is a way of describing juggling patterns. A lot of jugglers, don't need any of this. They have figured this stuff out naturally. Anthony Gatto, who saw it at the beginning, he just did his own thing. He described his tricks. He said, well, that's the over and under thing, the high-low thing. But he was a very top expert and had an intuitive feel, a fantastic athlete. So he didn't need a lot of formalism to approach juggling. But for the rest of us, kind of mere mortals, it helps sometimes just to have somebody else who has thought through things and gives us a little recipe, a description of different tricks. And turns out Siteswap notation is a really nice way to describe juggling patterns. So the first part is just a sequence of whole numbers, integers. So in Clojure, for us, that would be a vector, and these are just simple numbers. In juggling notation, we usually just write all the digits squashed together like a string, but we know implicitly those are separate throws. And the other aspect, in juggling, we start a pattern, we just keep the pattern going. So in Clojure, that would be a cycle, implicit cycle. So we have a finite vector, but implicitly, we're just going to start over at the beginning again and keep juggling. So as I mentioned before, throwing a 3 is just a simple cross in a 3-ball pattern. Similarly, like a 5 would just be a higher throw because you want to fit 5 balls in the pattern. So it's a continuous juggling, so every ball throws and then lands 5 beats later, or you're caught 5 beats later, and you throw it again. So 5 balls fit in that. 7 balls is hard to do, but it's the same idea of crossing. On the even patterns, like a 4 throw is coming back to the same hand, but throwing high enough so that we can alternate hands, 2 balls flying in each hand. And then higher numbers go up. Some good jugglers can do 6 balls, some even more. Special notation, the 0 in Siteswap stands for an empty hand. Okay, so sometimes just the way the pattern works, this hand doesn't do anything on a beat. The 1 pattern is just a quick switch. So if you could throw it quickly there, and then we're going to throw right away. So that's a 1 coming across. A 2 is a throw to the same hand, but it's a short throw. And it's so short that most jugglers will just do a hold. And sometimes they'll do something fancy and fly the ball around just to distract. And that's part of the showmanship. But a 2 just stays in the same hand, and then the next time this hand's going to throw, it's going to throw that ball. Okay, so this is a graphic borrowed from the Scientific American article, and we're showing a timeline to give you another feel for how those throws work. So the first throw was a 5. So at time 0, we're throwing the ball high enough so that it lands 5 beats later. At time 1, we're throwing the 3. That will land, since it started at time 1, we had 3 beats, lands at time 4. The third ball, throwing at time 2, 1 beat. It just lands at time 3. And then at time 3, that same ball, because we threw a 1, now we're going to throw that same ball goes again. Okay, so looking across the timeline, you can see the first ball has the experience throwing 5, then throw a 1, throws 5, and then a 1. The second ball, though, is just going in a 3. It feels every time it's thrown, it's a 3. So it's kind of in its own sub-pattern. Third ball goes 1, 5, which is very similar. Okay, so you can see how you can mix patterns here together, and if they fit in just right, we can juggle the whole thing. Now, not every combination of integers is going to be a good juggling pattern, and we want to talk a little bit about that. This is an important point. Let me come back to that. First, I want to give credit to the inventors of Siteswap notation. This goes back to '81, I think, the first one, Paul Klimek. But there were a lot of other juggling notations at the time. In the '80s, jugglers were trying to figure out, how can I describe my tricks so that other people can share it? We didn't have YouTube, so they didn't have an easy way to share videos and see each other's tricks. But they would talk about it, and these long-winded descriptions about fancy tricks where I'm throwing it over this way and then throwing that way real quick. It turns out that's not so precise. And the jugglers were doing their tricks. Okay, individual jugglers knew exactly what they were doing, but they were trying to communicate to other people. And there's a little bit of bragging rights on some of these things, like, I invented that trick first. Okay, well, I've been doing that for 10 years. So they get together at conventions like this, and people, I say I invented, conj way back when, before Rich Hickey even knew about Lisp. So they're arguing about their tricks. This is a way to succinctly describe your tricks with a pattern, and we kind of merged all these different ideas together where several of these inventors had their own notations and their own reasons for doing a notation a certain way. But when they got together and after some discussion and argument, they settled, oh, there's some nice mathematical properties to the way Siteswap that we know today. So let's get back to Siteswap. One nice property is that the number of balls in your pattern is just the average of all the elements in the pattern. So we can see the 5, 3, 1, add that up, divide by 3, and you get 3. Okay? The 7, 1, okay, it's only a 2-element pattern, but the average is 4. So that means there's 4 balls. You start juggling 7, 1, you can think about it. You threw that 7 up kind of high, and now there's a place for another ball to go. So that's the natural number of balls is going to be 4. Then the last pattern is a really complicated one, but we'll come back to that. And that's a 5-ball pattern. That takes a really excellent juggler to do that. But, okay, so this is a necessary condition that the average has to be a whole integer, but it's not sufficient. Okay? There's another thing to think about. There are some averages that will still produce collisions. And so we're trying to do a uniform juggling pattern. We don't want 2 balls landing at the same time. So how do we schedule a landing? We talked about this a little bit before, but the last line in this is, this is, I think, the biggest code part I'm going to show you today, so we'll take a minute to look at it. But the last line there, we're using map indexed plus on the pattern. So you think about the time sequence is the first argument. The order in the vector is going to be our time sequence. So the landing pattern for a ball is the height of the ball, or the number you're throwing, because that's going to land that many beats later, plus whatever time you're launching from. Okay, so that's pretty simple if you think about it. Collisions happen if we have 2 results that are the same number. So we apply distinct to the result. Now there's a mod on the count or the period of our juggling pattern. That's just to handle the kind of oddball cases where someone throws one really high. It's not going to come down right away, but it will, it just works out mathematically. It will re-enter the pattern, mod the number of throws you have. So if you do that and we have a distinct result, right, unique numbers in each place, then that's a juggling pattern that's valid in Siteswap. Now there's one other special case that I had to consider, and this is just my opinion, but if your pattern, what about the empty vector? Is that a valid juggling pattern? So I thought about that long and hard. Okay, there's nothing to juggle. Nothing to juggle. I decided meditation is the simplest form of juggling, so I will accept that. Okay, I'm not sure all jugglers agree, but I think it works for us programmers. So of course, once we have a predicate, it's natural. You have to do a spec, and we're at Clojure, so everyone has to show a spec slide at the conj. Okay, but it works out. And my spec here, I'm limiting my throws to 9. Great jugglers can do a little bit higher, but it's convenient for me. Okay, so I want to come back to another thing that I alluded to earlier about orbits. And this is a way to decompose some patterns into subpatterns. And the mathematicians have called those orbits. So the 5-3 pattern that we saw before, and we saw the timeline, you can think of that as a 501 pattern composed kind of by superposition with the 030 pattern. Okay? And then these subpatterns, though, are valid juggling patterns. You can juggle that, and you can think about like how many balls would be in the, well, we already said that there are 3 balls in the 531 pattern. That's the average of 531. What's the average of 501? Okay, so that's, everyone thinks about that and says, okay, add that to 6, divide by 3, it's 2. Okay, there's 2 balls that are following this 501 pattern. And the 030, that's 1 ball in that pattern. And this is really a nice property, and I know it's just kind of one of those beautiful mathematical things, and part of the reason Siteswap notation is interesting, I think, is that people, we're exploring, okay, I have these different notations, they all work, they describe juggling, but look at this nice property we have from this kind of representation. And it's a simple representation. It's a little bit of code to pull out these orbits, but it's only a page of code, it's not a lot. And it just, it's very pleasing, I think, for me. At least I think mathematicians like this kind of thing. So we can extract another pattern I show here is 4413. And that's not even like if you're not a juggler, that's not obvious. Well, what is that pattern? But you can think about basically there's a 4 in each hand going up and down, and then there's one ball just going back, going a 3-1, 3-1, doing a little circle here. Now, I'm not actually good enough to do that juggling, especially kind of the night after the party. But that's a nice little pattern, and kind of regular jugglers that really are dedicated can do that. So you can see there's, first of all, the 4413 is a 3-ball pattern. Okay, you can just take the average, and you can see there's 1 ball in each of those orbits. And the last one is more complicated. We'll look at that again separately. The other advantage for jugglers to doing this kind of orbital decomposition is that they can practice the orbits separately. Okay, so there's an advantage. We see this in software all the time. You want to decompose, pull things apart, because then you can understand them as individual things, and you can, in this case, for jugglers, you can practice. You can get good at doing the 501. You can get good at the 3. That's pretty simple. Then you can put those together. Okay, so you know things about these subpatterns, and you kind of get a feel for how that fits together in a larger pattern. And I think we experience that in our software too. So even though juggling's complex, there's a hidden simplicity in there, or something you can pull out. And I hope we try to do that with our software. So I want to turn this now to doing a little bit of programming. So after thinking about these patterns, oh, that's pretty cool. I'm not a good enough juggler to do all these patterns, but maybe my computer can figure this out. I have Clojure. I found the Quill library has been spoken about at several of these conferences. It's a convenient graphics and animation package. Runs on Clojure and ClojureScript. So I grabbed that as my first Quill program. So I made a little package called Rastelli, named for a famous old juggler. And then I made some animations, and just for this talk, I made a little movie and put them on the slide. So I'm not doing live coding right now, but it would work, and I'll let you have my software later. But this is a 453 pattern, which is another beautiful pattern, 4-ball pattern, and let me run that. And you can see the balls running, and one nice thing I like about Rastelli is showing these orbits. It really helps you think about where the balls are going. Gives you a better feel. If you just see them flying around in space real time, it's sometimes hard to pick out the orbits. So I just draw a little trace for you. Okay, and then one more example, just because I really think this is a beautiful pattern. We have 3 different orbits here. The balls are flying around, and it just, to me, that's just kind of almost art. I could enjoy just watching that. I'm glad I don't have that for a screensaver. I'd never get anything done. Okay, excuse me. Okay, and then this is a really interesting pattern too, because you can see 2 balls in this 901. Okay, that's basically a really high arching pattern. Okay, so you can see the high arches, and then you can see the low, the ones just coming right across. Okay, so they're alternating and going across like that. But that, I could do that. Okay, I can do that orbit. So I could imagine working my way up. It's not easy. This would take years for a good juggler to learn. But I could start on it, and I'd get a feel for it. So I can pull out pieces and do some of these individual pieces. Okay, let's get back to some more ideas about our patterns and what we can do with patterns. So first of all, there's isomorphic patterns, and this is like just kind of obvious, but you can repeat a pattern, and that's natural in juggling. So the 3-ball cascade, if you just keep doing it, you can call it 3, 3, 3, 3. That's all the same pattern, right? Same shape. If you rotate, instead of doing just 5, 3, 1, you do 3, 1, 5. That's still a valid pattern. It's just kind of the mirror image because it's we shifted 1, so we're starting on a different hand, but it's the same shape of pattern. Okay, so we call those isomorphic, and we know those are valid patterns. If we've already established that one pattern is valid, and any of these changes are still valid. Now, how would you make new patterns? Okay, so the mathematicians did some research here, and the first way, a simple way, is add the period to any one element, and that creates a new but valid pattern. Okay, you don't have to think about it. This has been proven to work. So if you have 3, 3. You can add 2 to that first, because there's 2 numbers in it, so it's a period of 2. You can add 2 to the first element. A 5, 3 is also a valid pattern. It's a different shape, of course, but it's valid, and it's something you could transition to from the first pattern. You can get to the second pattern. Okay, the juggler can add a trick or do something a little different while he's juggling. The more general case is what we call swapping sites, and that's why the name Siteswap comes from the idea I can make a new juggling pattern by taking any 2 elements. I'm going to swap places and do a little bit of math, and that math, okay, so we're swapping two spaces. They're a certain distance apart. The one that I'm bringing forward in time, I have to add the distance. So if I had a 3 at time 2 and bringing it to time 1, I'm going to add 2, right? Because I go from 3, I move 2 spaces. I'm sorry, I'm adding 2 to the 3 and getting 5. Okay, so at the bottom we have an example there. The first 3 started at time 0. I'm moving that to time 2, so I'm going to subtract 2 from that. So I go from the 3, 3, 3 pattern to the 5, 3, 1 pattern. I know that's valid. Okay, and we already know the degenerate patterns, the single number patterns, are all valid. Those are the base juggling patterns, just a 3, just a 4, just a 5, that kind of thing. So then we're creating new patterns from those base patterns we already know. And we can keep doing this, swapping different elements, adding the period. You can generate a lot of interesting patterns just from that. And we know we can transition from one pattern to another. It's kind of like lining up your parameters and just knowing that all these things fit together when we're programming software. Jugglers have been doing this for a long time. Okay, and the reason this works is because we're guaranteeing the same landing pattern. Okay, so you can see how the math works on that. It's simple math, but it's kind of one of those insights. Once you see it, you say, oh yeah, that's easy. But it wasn't obvious at first to everyone, and people had their different notations. So they finally said, that is mathematically elegant. So I want to come back to this slide and thinking about the 5, 3, 1. So now that you have a little bit of coaching, you can see the periods in there, right? 2 different periods. You can see what happens, say, if you swap the 3 and the 1. Right, so like we're throwing a 1 at time 2, and we're going to pull that forward in time. So now we have to throw from time 1, right? The 1's moving forward. We'd have to throw a 2. The 3 would move back in time. We'd have to subtract from that and make it. Well, that's a little different example. Sorry, but anyway, we have to switch the values there as you rearrange these. Maybe a better example, I guess, is switching the 5 and the 3. We showed you can pull the 5 and the 3, just change their order, subtract 1 from the 5, you get a 4. So now we're throwing from time 1, we're throwing the 4, but it's still landing at the same time, at time 5. Okay? You can also see how if you just rearrange the numbers, you could have problems. You can have collisions. So if you throw the 5 at time 0, that lands at time 5. If at the second place, or say the third place, at time 2, if you threw the 3 at time 2, okay, that would also land at time 5. So that would be a collision. So that's why 5, 1, 3 is not a valid juggling pattern. Okay, it still averages out right, but we have the collision at the landing site. Okay. So the mathematicians thought a lot about this idea of mapping your landing sites, and that leads to the idea of doing a state transition diagram for juggling. The states now are when you expect a ball to land. And so it's a vector of bits. We're using 1 for something. We expect something to land at, the first element is time 0. We've been juggling. We're in a steady state. We expect a ball to land at time 0. We expect a ball to land at time 1, at time 2. That's the standard 3-ball juggling pattern. If you throw a 3, right, the first ball comes out of the pattern, you slide everything forward, and now you drop a 1 in the old state, you end up getting in the same state. So throwing a 3 is just a steady, you stay in the same state. If you throw a 5, that ball's not going to come down at time 3 anymore. It's coming down at time 5. So now we leave a hole in the landing pattern. So you can see in the diagram, if you start from kind of the upper right side on your screen, 1, 1, 0, 0, the 3 keeps you in the same state. You throw down to the 5, you get to the new state, and that's 1, 1, 0, 0, 1. Okay, and then once you're in any state, we can work out all the transitions that are legal and to keep in a juggling pattern. And these are all the tricks that you can do from a 3-ball pattern, limiting yourself. I only want to throw up to a 5, so I'll throw 0 to 5, and now we've considered all this. So we get a nice state transition diagram here. And I want to put this into Loom. I haven't quite gotten to this, but I'm going to put this into Loom or do a little graph analysis in Clojure, and then use a state diagram, a state machine like this, to power my juggling simulation. So now my little Rastelli juggler can do his standard pattern that you gave it, but then you can say, okay, show me, put on a show here, and it knows the valid transitions, it can make other throws, and you can get really interesting, complex patterns just from these very simple rules. Okay? And so, I mean, I want to just review the Siteswap features and try to connect that to some of our software efforts. So the first thing is we're starting with simple data representation. I think Clojure programmers all love that. And Stu Holloway mentioned systemic generality. Well, jugglers have been doing that for a long time. We're using this simple integer notation, and it's easy to grasp, easy to communicate. We'll get to that. Also allows for a flexible interpretation. So when we're talking about a 3, my 3 pattern might be a little higher than like a super experienced juggler who can do a really quick low 3, but they're still the same basic shape. And a 5 for me is relative to my 3, so it's higher. But we're not giving a precise number, like how high you're throwing it, how fast you're throwing it. You just want to let the interpreter, the juggler, do his own thing. That also means our programs. I can represent juggling the way I want to show juggling. And when you saw my little diagrams, I was not physically correct on everything. I had a little compression in my height to make it fit better on the screen. But the timing felt right, and it gives you a good sense of how that juggling pattern would work. And I think any experienced juggler would recognize those patterns and be able to try to recreate them. So flexible interpretation is another good element to have in our software. We talk about, we might be communicating with other systems, and we're not always in the Clojure world. But a simple data representation and flexible interpretation, just a little bit of common knowledge, just to know, like, we're in a juggling context here, is enough to let somebody else do something with our clever tricks that maybe they had never thought of. As I said before, sharing, jugglers originally started this notation so that they could conveniently share, talk about what they were doing. I think that works well in our programming world too. We want to share data. Sometimes we want to share code too, but sharing data is really important. Composition, all the Clojure programmers care about being able to compose their programs. We saw in the juggling world, we have composition of subpatterns to make one pattern. We have these transitions that let us extend juggling routines, so we can put things together in different ways and we know they're valid. So composition is another kind of motivation you can get from examining juggling. We saw at the beginning verification. That's an important idea. You can give me any pretty much random set of integers. I can verify whether that's a juggling pattern. I didn't get into it, but there's also another theorem that says, give me any random sequence of integers. I can search through that and find a valid juggling pattern. That's a more advanced proof. But you can imagine just brute force. We can go find that. And that's really an interesting result. And then the last item here is generation. So we're all really excited about test.check and now Spec with being able to generate new data from old data or descriptions of the data. And the same thing helped jugglers. It was, I think, really exciting when the jugglers said, I'm not only describing my current patterns, I found a way to describe all the possible patterns. Given 3 balls, now we know how that works, and you can expand that to more. And that's something they discovered after they came up with their notation. Okay, this was not like, oh, I wonder, how could I describe all juggling patterns? It wasn't like that. They were juggling, they wanted to share, and then a few mathematicians said, well, wait a second. Now that we have this, we've pretty much examined our whole space of juggling in the simple uniform juggling. Of course, there's advanced notation for doing multiplex juggling and other like tricks beyond the uniform pattern. But still, I mean, I get a really good feeling from having the generation capability just at the simple pattern. And I think that's a lesson we've, I think, internalized in the Clojure community, but generation really is a valuable property, and we want to work hard to examine what happens when we generate new patterns. We use it for testing, but we saw the talk yesterday about music, and he says, well, what if we just let the computer generate some music? And that was really fascinating. So there's a whole world to explore here with generation, and jugglers have been doing this for about 35 years, so we have some catching up to do. Okay, I want to give you a few more resources. If you're now interested in juggling, I don't know, maybe you've been juggling, you probably already know this, but if you want to pursue juggling, juggling.org is a great website. The WJF, if you're more into the sport of juggling, they have what they call combat juggling. They have where people try to knock each other's clubs down. It's competition. That's kind of fun to watch. I never would have thought of that myself. They have joggling, which is running and juggling at the same time, and they have their own events there, where these guys are good. And it's a sporting activity, but it's just a fun kind of hobby. Wikipedia is a great source for lots of juggling information. All the jugglers and mathematicians contribute to Wikipedia. Then there's a couple of other sites for people who have been doing juggling programs for a long time. So I'm really late to this game, but I'm going to do my own spin on it and do some Clojure. All right, now I want to give you some other math resources. If you want to get into the mathematics of juggling, somebody wrote a whole book about the mathematics of juggling. You can get into group theory and topology, lots of sigmas and subscripts. I mean, you can go to town in math. Go look up this book by Burkhard Polster. He's at Monash University in Australia. He also published a survey article, which is a great article. I recommend you read that. You can read that one for free. You don't even have to buy the book. And the same Burkhard Polster has done some videos on juggling on the web. And he has a great quote here: the way I feel when I look at a nice equation is the same way I feel when I look at a nice juggling pattern. Okay, so that's the mathematician enjoying juggling. And I kind of enjoy his spirit. He's a lot of fun if you watch some of his videos. Another great juggler, a math professor at Cornell, Alan Knutson. I hope I pronounced that right. He wrote the frequently asked questions summary for Siteswap Notation that is on rec.juggling. It's been there for a long time, over a decade. And he has a fantastic video where he goes through all the Siteswap possibilities. He's an excellent juggler, so he can illustrate everything. I had to use my software to illustrate some of those patterns, but he can do it. And so look him up on the web. That's still another great video. Now, I'd like to change gear. I think I have a few minutes. I want to just mention neuroscience. This is kind of beyond my area of expertise, but I just happened to come across this, that the neuroscientists are really excited about juggling. It turns out, I'm stealing some slides here from Mark Hott, who's talking about recent developments in neuroscience, and especially about brain plasticity. So it turns out they've done some experiments where they trained people in juggling. They had a control group who didn't learn any juggling, and then another group who didn't know juggling before. They learned juggling. After a few months, they did brain scans before and after, and they noticed an increase in their gray matter in their brains. So they could see brains changing due to learning. And juggling, it turns out, is just a good kind of task. I mean, in theory, you would see change in your brain from learning a foreign language or learning to play a musical instrument. But those tasks take longer. You can teach people juggling at least 3 ball patterns pretty quickly, and they're excited because now they can see changes in the brain. And that kind of study was repeated. They got similar results. This was even after a week. They could see the changes in the brain of people who had learned to juggle, and they want to explore that. I mean, this is a great technique now with better scanning technology. this kind of task to learn and to see the changes in people's brains is really exciting for the neuroscientists. They also did another follow-up study beyond this with older adults, and they see similar results. So even, we used to think that, as you got older, basically you're just losing brain cells and kind of a slow downhill slide for older folks. Well, the good news is, no, you can learn things. You will acquire more gray matter and white matter, get more brain power just by learning new tasks. So old dogs should learn new tricks. It's still worthwhile. And in this kind of similar vein, just the benefits of juggling for real people, I came across this talk from Jennifer Slaw. She has a series called Juggling Life, where she teaches people to juggle. And reports, just anecdotally, but I kind of believe her because I like juggling, but people have improvements in their memory and concentration, flexibility, patience. It takes a while to learn how to juggle. Balance, and most of these are good properties for programmers too. So I say, why not try a little juggling? She has a heartwarming story about teaching a homeless girl who was in a shelter how to juggle. And you think, well, that's not really important for somebody in a shelter to learn how to juggle. But she reports that this girl thought juggling was impossible. She could never do it. And just with a little bit of coaching and mentoring, and maybe it helps that somebody took time to be with her, but the subject was juggling. She learned how to juggle, and she got a tremendous sense of accomplishment just from learning how to juggle. And we hope that might carry over to other parts of someone's life. If you get a coach and you learn how to do something that seems impossible, and then you accomplish that, you get a sense that you can go do a lot of other things. So anyway, I really recommend this video. She's a good speaker and kind of a fun story. So finally, I want to just mention Michael Motion, who's a fantastic juggler and a true artist. He uses excellent juggling skills to explore rhythm and dance and music, and just he has a great artistic sense. So if you lean more towards the art side of things and less towards the math, you might like to look him up on the web, just some really inspirational videos. And he was talking about juggling. He said, what you learn is how to feel with your eyes and see with your hands. And so to me, that kind of expresses the zen of juggling. And if you're a juggler, that might make sense to you. And if you haven't juggled, try it. You might learn something or have a new experience there. So to recap, juggling has inspired mathematicians like Claude Shannon over the years, and I think we can learn a lot from how they approach a complex subject like juggling. We reviewed the Siteswap Notation, which I call a juggling DSL, and I tried to make some connections to our experience as software developers from how the jugglers approached their problem of communicating their juggling patterns. And then we found some interesting mathematical properties that derived from just having a simple representation. Then the third thing is I've written a little Clojure library that simulates juggling called Rastelli. So Clojure is really useful for a bunch of things. So if you still doubt that juggling is relevant to programmers, I just want to point out this painting recently appeared on Classic Programmer Paintings. I have no idea how it got there, but it's just good timing for my talk. So yeah, juggling does apply to programmers. And I want to thank my Beagle. He reviewed an earlier version of this talk. And finally, I just want to say, juggling is fun, and anybody can learn to juggle. So let's take a look at my friend here. Okay, thank you very much.